Every edge that's missing in here will be part of the complement. Those edges in the complement are of two kinds. There are the edges that are missing inside a component, like in here. This edge is missing, right? We all see that? This edge is missing. That edge will be part of the complement. But there is also this edge that is missing from here to here. So this is U, V, and Z. VZ will be part of the edge complement. This G is V, the same V, but the edges are the other edges. Also, UV will be part of the edges of the complement, right? Because they are missing in this graph, therefore they're part of the complement graph. So now why is the complement connected? Any two vertices that are in different components, what's going to happen with them in the complement? There'll be an edge, right? Any vertices you pick in different components, there will be a direct edge into the complement because that edge is missing in the original graph. What happened with two edges in a one component? Two vertices, sorry. So if I have two vertices, if U, V are part of different components, then the edge UV is guaranteed to be into the E bar. We already said that. Now, if say VZ are part of the same component, maybe if they are disconnected like in here, clearly they're going to have an edge in the complement, right? But what if let's say not VZ, let's say VT. What if this VT, well, they had an edge in between. Are they going to have an edge in the complement? No. But why are they still connected? Why there's a path? Because they both connected to U, right? This edge UT and UV, they're going to be part of the complement graph. So if they're in the same component and U is in a different component, then UV is part of the edge bar and UT is part of the edge bar. Therefore, there is a path from V to T in G bar, in G complement. So you can see that if two vertices are in the same component, there's a path. If they're different components, there's a direct edge. Therefore, the complement must be all connected because every two vertices are connected. Just want to recap that. I know people have run home, asked questions about it, so on and so forth. Just make sure everybody gets the problem right. All right. So we are behind by one lecture, which means I have to, put up a show here for today. The good thing is about this is an easy stuff. A lot of this is secondary school stuff, so we can get through it very quickly. We're starting a new thing today. One would say algorithms are more computer science-ish than pure math. That's not quite true. Algorithms have a lot of math in them. But it is true that it brings us more to computers. Algorithms is what we need to write computer programs, right? So the first thing I want to establish is, before we do, algorithms have a lot to do with technique. Or strategy. But they also have to do with memory and data representation. And they also have to do with hardware. Things like CPU, GPU, so on and so forth. So a lot of algorithms, will say algorithms in computer science, both in this class and in the algorithms class and later in the theory class, we mean the technique, right? Like how do you go by and find the minimum, the maximum, the median, all those problems. What's your strategy? How do you think about that? And you can add here maybe implementation. That may have to do with the operating system and programming languages. Like once you have an algorithm, how do you actually write it in Python or in Scheme or in Java or in MATLAB or whatever language you want? There might be some issues there too, which of course are part of computer science, but typically they study in different kind of courses like programming languages courses. So this is the most important thing for us. What's the strategy to go by and do stuff? And usually this determines what we call asymptotic time. By this, or runtime, asymptotic runtime. The reason we like the asymptotic runtime as opposed to the real clock time, if I ask how long it's going to take to run this algorithm, that question is a well-defined question and has an answer in minutes and seconds and hours, right? But those minutes and seconds and hours depend on so much more, right? It depends on what kind of CPU you have. Is it a fast one or a slow one? How many threads can it handle? How well is it implemented? Is it in a fast language like Java or C++, or is it in a slow language like Python? How you handle memories and stuff. So in order to exclude those issues from the algorithm's time, we call this asymptotic time, which is more like a growth time. This is roughly means growth with input. It's like saying how much, if it takes for 5 items, my input of 5 items, it takes that many, units of time. How is it going to take for 20 items or 60 items? How does it scale when the input grows? Okay. Now, that's something we're going to do, of course. And the other thing I want to establish, which is very important for everybody, and most of you already know it, I won't talk about memory much, but I will want to start with a distinction between arrays and lists. So in an array, say we call it A. I'm going to write an array as a chunk of things, and I'm going to say in here, the values goes inside. So my values here are 50, 5, 32, 2, 16, 50 again, and 40. Too long. So those are values. And if I want indices, I can put the indices here. 1, 2, 3, 4, 5, 6, 7. Those are indices. Sometimes we don't write the indices because in an array, indices are from 1 to whatever. Some people start the indexing from 0. Just like with sequences, that's fine. If you want the first one to be 0, that's fine. When you implement an array in an actual programming language, you have to stick with that language. Some languages start from 0, some languages start from 1. If you do MATLAB, you're going to have to start from 1 because MATLAB doesn't allow index 0. If you do C++, you're going to have to start from 0 because that's the convention C++. But on the board or on paper, we can choose whatever indexing we want. Just like with sequences, the sequence is the same, but you can start it from 0 or start it from 1. I'm going to start from 1 because I like to start indexing from 1. But if you want to start from 0, it's no difference. So those are indices, and we can say A of 2 equal 5. Okay? That means array A in position 2 has the value 5. Okay? In a list, the same data could be represented as, here's the head of the list. And that's the value 50. It's an object in memory that's 50. The next one is a 5. The next one is a 32. The next one is a 2. The next one is a 16. 50. And 40. In a list, we typically have to put a little sign here. Sometimes it's a square like that. This square means null. So if you see null, it's the same as the square. Because we need to know when the list ends. For arrays, we don't need that. For arrays, we have a meta information, so to speak. There's something stored how big the array is. Many languages have a field in an array, and a meta field that says this array is allocated for 7 chunks of memory or 20 chunks of memory. So you can tell how big the array is. In lists, typically we don't know how long the list is. We have to go at the end and say, hey, is there a null coming up? Because if there's a null, that's the moment when the list ends. Now, this is one chunk of memory. It's a contiguous chunk of memory. This is not. These pieces of memory, even though you don't know how memory works, these are not in the memory one after the other. They could be spread in your memory all over the place. So this is different parts of memory. So arrays are good for, I know exactly how those objects I have. In my case, the objects are numbers. So if I want to have 4 bytes numbers, that's 32 bits. I need to allocate 32 bits for each object. If you declare an array of integers, by default, you get 4 bytes for each integer. So if I say, give me an array of 7 integers, how many bits I get allocated? In typical programming languages, I say, give me 7, I want an array of 7 integers. Integers are typically 4 bytes. How many bytes I get allocated? 28 bytes. If I measure that in bits, I know, so this will be 7 times 4 bytes. That is 28 bytes allocated. I have to specify this. When I say give me an array allocation to a programming language, I'm typically going to say how much memory do I want for it. Even though I don't use necessarily all of it in the beginning, I have to do it. In a list, I don't have to allocate all the memory in advance. I can deal with the numbers I want, right? The list I want. And if I later on want to add something to it, because it's not a contiguous chunk of memory, I'm going to say, give me another, allocate another object for me memory, another 4 bytes. Doesn't have to be next to this list, whatever else. And I'm going to link. There is a linkage that tells me from here what's the next chunk of memory that you need to go to. In an array, if I want more data, I can't just write it here. Why is that?
The array is not
That may be allocated to something else. And arrays have to be contiguous. I can't just put the array somewhere else and say, that's a whole array now. Arrays have to be contiguous chunks of memory. Many programming languages rely very critically on this information. Because it's a contiguous chunk, it could be accessed randomly, right? Can I just say A of 2? How does the computer know to go to A of 2? Yes?
Starting index plus 2 times the size.
Right, he says, I know where the array starts. I know what's the size of each object is 4 bytes. So A of 2, I go from the beginning. That's a memory location, right? It's a hexadecimal memory location. It knows exactly where it needs to go. How many I need to go forward? I need to go 1 forward, right? If I say A of 4, I need to go from here 3 times 4 bytes forward. So I can compute immediately in an array, given the starting memory. This is the memory address of the array, right? This is the memory address. Or the head. You can call it the same like the list. That's the head. In here, if I know each object is 4 bytes, and I want the 4th object, I know I need to move forward. This is plus 12 bytes, right? From the beginning. And because it's a continuous chunk of memory, plus 12 is going to be exactly that. So I can access elements like this, random. In a list, I can't do that. Can I say, give me the 4th element of a list? What do you have to do to get to the 4th element of a list?
Go through the first and the second.
Start from the beginning and see where it takes you, because those are different parts of memory. The only way to get to here is to say, okay, start here, move to next one, move to next one, move to next one. That's just moving through the memory and then gets in here. So there's advantages and disadvantages to both things. That arrays can be addressed in constant time randomly, but they have this constraint. They have to be contiguous. You can't really enlarge an array that easily. Lists, on the other side, they jump around in memory all over the place, but they can be addressed in constant time. How about insertion? If I say, I want to stick an element between 2 and 16, I have another value I want to put right here. Insert. What do I have to do in an array? I have to make space for it, right? Both in array and list. How would I make space in an array to fit a value in the middle? Yes.
Move all the following.
I have to move a lot of things, right? To take all this stuff and move it somehow. Maybe even reallocate the array, right? If I don't have enough space, I'll have to get a bigger array first, move everybody around. How do I insert in a list? If I want a value inserted in a list, how do I insert it here? Yes?
Make the one before it point to your new element.
Right, I create a new element, whatever the value is, say the value in here is 19. I destroy this link. I leave the list as it is in memory. I don't change nothing, right? I destroy it and I say what? This one now points in here, and this one now points in here. I just did these pointers that tells me where in memory is the next object. That's a pointer, right? So, but that way I created my new object, the list is in place, all I did is destroy this pointer and redo the linkage of the list. Much more easy to insert something in the middle of the list than in the middle of the array. In an array I have to move stuff around. But there's disadvantages to lists, as we're gonna see. Hands up who's with me on arrays versus lists. I hope some of this is clear from before, but there's other data structures, of course. There are lists and arrays. There's stacks, there's trees, there's heaps, there's all kinds of things. But those two things are the basic two data structures that you're going to use 90% of the time. Most of the stuff we do is with arrays and lists. So now our first algorithm is linear search. Either in list or array. So I suppose I have an array or a list, and linear search means what? Find value b equal, let's say I want to find 16. I want to see if my list or my array contains the value 16, and if it does, I want to know where is it. So here's the linear search. It says start from the beginning, right? So it's loop start in the beginning. Either array or list. And there's a loop that says is the value, is current value equal the value I'm looking for, b. Is if yes, then done. I found my value. If not, move to the next element. So I'm looping this until end of list or array. I don't want to be very formal with this pseudocode. You guys are going to take algorithms and you're going to learn how to write this better. I prefer for now writing stuff in English. Okay, what's going on. So it's very easy to see what's going on. I start in the beginning or either one of the structures. I know the value I'm looking for, 16. I compare the current value with 16. If it's 16, I'm done. I found my value. If it's not, I move on. In an array, how do I move on again? I have to have some index, right? Move the index I equal I plus 1. So moving on is different from an array. How do I move on? I make I equal I plus 1. That's the index. In a list, how do I move on? I go to the next, I can say the object is the object I'm looking maybe point next or dot next or whatever the mechanism is to go to that link and get to the next element, right? In an array, it's easier because array is indexed from 1 to 7 or 10. I just make the index from 3, I make it 4. It's like an induction, right? From 3 you go to 4, and then you got the next value. Okay, how long is this gonna take?
As long as how many inputs there are.
Right, so the runtime of this, again, we're talking about asymptotic runtimes. We don't measure the seconds here or the minutes. We just say it's a function of the array length, right? Obviously, this is going to take longer for longer lists. What's the, in my case, my array and list have size 7. What is the maximum number of steps it could take?
7.
7. What's the best, the minimum number of steps it could take? 1, just in the beginning, right? So it's a function of the length, obviously, but there are 3 cases. Is the worst case, it's gonna be about, so let's say the size of the array, which is the size of the list, is n. That we're gonna call the size of input. It's, in this case, is the number of elements that I'm looking through, right? In the worst case, it's n, because I have to go through all of them. I could have a value that's not in here. Suppose I'm looking for 100, I'm gonna have to go through the whole array and see, you know. So when I see end, I have to do something after end. In the case I found the value, I'm gonna output the value and say done, right? Meaning done, output the index I or the object, where I found that value. But if I'm here and I'm not done, meaning I didn't terminate, what does it mean if I ended up here on this end statement and I'm saying you didn't finish? What does it mean? Not found. So I can say done here as in not found. Because I finished the loop and I didn't exit with the yes, print the value. Ends up with me, with a not found. Good. So worst case about n, best case is about what? 1. And how about an average? If I'm telling you I'm looking for a value, it could be anywhere, equally likely, anywhere. But I'm telling you it's in. So, because if it's not in, it's guaranteed to be in steps, right? If it's not in, I have to traverse the whole array. Average, if it's in, if value belongs to the array or the list, right? Assuming the value is in there, on average, if it could be anywhere, what's the average number of steps it's going to take? Yes?
L over 2,
N.
or N over 2.
Right? On average, it's going to take half of the steps. Why are we saying this? If you know a little bit of statistics, we're going to say, well, there is the average of where it could be, right? So there's a uniform average, which is, it could be in 1 step, or 2 steps, or 3 steps, or n steps, right? By n, it could be in the first spot, second spot, third spot by n. That's roughly n plus 1 over 2. N plus 1 over 2 and n over 2 mean the same thing for us. Because we don't measure this exact time, but we measure the asymptotic time. I'll get to that in the second part of the lecture. Why n over 2 and n plus 1 over 2 means roughly the same thing. This is an exact calculation. This is a more approximative, it's half, about half on average. Do we understand the difference between best, average, and worst? Worst is like the mechanism I'm looking for it's unlucky for this particular case. I have to go through the whole array until I'm done. The best is when I found something quick and I'm done. I'm lucky. And average is, well, sometimes I'm going to be lucky, sometimes I'm going to be unlucky. Assuming I don't have an adversarial feeding my inputs, I always get unlucky, assuming the value I'm looking for could be anywhere with equal probability or equally likely, is roughly n by 2. How about if I'm looking not for a value, but I want the maximum? Is it the same thing, the maximum? It's a different algorithm. What's different about it? Yes?
You basically have to compare pairs of inputs and then store the one that's
So how do we do that? Maximum of an array or list. I have no value as input. In this algorithm, linear search, I am given a value. Find this value. In the maximum, I don't have given any input, so how do I say? I say, I declare max to be the first one, first value. First value, it's either a of 1 or the object equal head of the list, right? In an array, in a list, it's the first object. And then I say loop again, right? Like in here, loop, when I'm done. And I say move to the next element. Move to the next value. If the value I'm reading now is bigger than my current maximum, I have to update my maximum. Maximum is the value, and the index, it's either the current I, so this is I goes to I plus 1, or object goes to object next. Next. This is depending on whether you do it with an array, with a list. In an array, you move to the next index. In a list, you move to the next object. So index is either the I or the object, depending whether you do an array or the list. I want to keep track where the maximum is. So I have to update the maximum. So that's an if statement in here. And when I'm done, I have to output the value, that's the maximum, and the index where it was found. Right. So what's going on in here? I have essentially the same loop. This loop traverses the array or the list. It declares the first one to be the maximum, and then it says every time you see a value bigger than the current maximum, update that maximum, and keep track of where you found it. Where in the array or in the list you found that maximum. And when you're done traversing the list, am I guaranteed for this to be the actual maximum of the list? If at every moment I said, if I found the bigger than the maximum, update the maximum, keep going. At the end of the list, am I guaranteed to have the maximum? Yes. And I can output, here's the maximum, and here's where you found it. In my case, what's the maximum here? Which 50 is going to be by that algorithm retrieved? Is it going to be this 50 or this 50? Why the first 50? Because it only updates if it's strictly larger. The second 50 won't cause an update because it's going to be 50, it's bigger than 50? No. What if I put bigger or equal than? Which 50 I'm going to output now? The second one, because the second one is going to cause an update. And for the index, in an array, I'm output is 6. And in a list, I don't output an index, I output the actual memory address of that object. The OOBJ, that's actually a memory address. Where is this 50 located? It's a hexadecimal number with the memory address where this object lives. Good. So we're going to say this is a linear, either one of this is linear. We're going to say everything that has n. What's the worst case in here? Worst case is the same as the best case. Does it matter for this algorithm whether the maximum is in the beginning or at the end or in the middle? How many steps are going to take here? N steps. So that's all cases is n. We're going to call this theta of n. And I'm going to talk about later what that means. But this is the runtime that we're looking for. Theta of n. This is also going to be theta of n. Even though it's a smaller n, it's n by 2, still counts as theta of n. This, in fact, means linear in n. This, which is also n by 2, it's also linear in n. But this is not linear in n, this one here. This is going to be theta of 1, which means constant. In here, we have theta of n, because it's a linear algorithm. I'm introducing this notation now, and before the lecture ends, we're going to make clear what it means. But for now, it's an informal notion of this is linear. What happens? So can I do the maximum any faster? Is there a way to get the maximum faster on an array than going through the whole array once? Is there? Right, if the array will be sorted, it's easy to get the maximum. Where is the maximum? At the end, right? I don't have to try nothing. I just say, give me the last element. But in general, if the array is not sorted, there's no way to go faster than linear. You have to go through each element once, which causes a linear algorithm. So now let's do the sorted array. Suppose I have the same array, but it's sorted. So how is it going to look if I sort that array? What's first? 2 is first. Then what? 5. Then what? 16. Then 32. Then now this is sorted. You have to know when you program something, when you get in your program, okay, I'm going to do something like a search or sort or anything, if your array is sorted or not. That makes a big difference. If it's sorted, that's great, but you got to make sure it's sorted. If it's not sorted, you don't have to worry about it. You can deal with any array, but then you can't make an assumption that it's sorted or hope that it's sorted, right? So it's either sorted or unsorted. If it's sorted, you got to make sure it's sorted to apply the thing. Now, how about the max? I don't need an algorithm for max. It's A of, I'm going to say here last. This is not very computer scientist, not very mathematical, but you know, everything goes in here. Last is, I could say maybe more formally A of n, because I know there's n elements, right? I'm going to say the size of A, which in here means the length of A is n. This is the input size. When I put an array into bars like this, I mean the length of the array. It's not a set. I mean, it's similar to a set notation, how many elements are in there. So I could say that maximum is done. How about find a value? Find value v. What v we're looking for? V equals 16. And here we just say, this is an additional input parameter for my algorithm, which value I'm looking for. I could still call this. This works whether it's sorted or not. Doesn't matter if it's sorted, it's going to find me the value. Can I do something faster here? If the array is sorted, can I found it faster than in n steps? Yes.
So now we can do a binary search.
Right, so how does that work?
Or we
So he's proposing faster than n means, let's be clear on this. If I want to do something significantly faster than linear, I don't mean n minus 1 or n minus 2 or even n by 2. All this stuff is going to be linear. It has to be significantly smaller than linear, which means that we're not going to look at all the elements, right? Because if we look at all the elements, how much time we spend just by looking at the elements? That's a linear time, right? You have to look at every single element. So to do it faster than linear means there'll be some elements we don't even look at them. We don't know what value is in there. So how can we find a value without looking at all the elements? We somehow must know that if we decide not to look in here, the value cannot be there. So how do we do this again?
So you start at the middle, and then if it's larger than the number you're looking for, you just look to the left. And
If this is larger, right? So he's saying, here's the middle of the array. Let's just say 1 plus n by 2, something like that. That's the middle. That's the middle index. And then what he's saying, if a of m, the value in the middle, is bigger than the value v, then you're saying look to the where. If the value in the middle is bigger than the value I'm looking for,
then you only look at the left half.
it means if it's there, it can only be on the left side. It cannot be on the right side, right? So it says search on left side. In other words, ignore the right. And if not, I'm going to say else. Everybody knows else. Else is the other case when this condition doesn't happen. So I'm going to put it in parentheses. That means A of m is smaller or equal than v, right? If it's not bigger, it's going to be smaller or equal than v. Then it does what? Search on the
Right side, or
right side.
if the elements are equal, and terminate.
Okay, let's do another thing then. Say we only deal with small or less. We don't include equal. And else, that must be the case. AM equal V, right? Then we say what? Done. Done. Output found at index M. Right? This is ignore left side. Now, I need everybody to be with me, so I'm going to ask twice about the hands. Once on what is exactly ignoring means. Ignoring means I've already decided the value I'm looking for is not on that side. So if the value, for example, is, I'm looking for the value 5, when I compare 5 with 32, I get 32 is bigger than 5. Therefore, which side I know for sure I don't need to look at? The right side. Because the right side is bigger than 32, and 32 is bigger than my value. So there's no point looking for that value in all these sides. That's where I'm getting the time, the runtime decrease, right? The whole half of the array, I'm not even going to look at it. So the similar happens on the left side. If the value I'm looking for is bigger than 32, 32 compares negative, like smaller than the value I'm looking for, then I know it's not on the left side. Therefore, it must, may only make sense to look for in the right side. Hands up, who's with me on this? Sounds easy, but you gotta be clear on it. The other issue that I want to ask you about is I clearly did it for arrays. Can I do the same thing for a list? Can I replicate this sort of algorithm? Look in the middle, compare the value. If it's smaller, go left side. If it's bigger, go right side. Can I do that? Why not? What stops me to do that? Yes?
The list doesn't independent length, so how do you find the middle value?
There is a middle value, right? There is a tool that's whatever. If I can get this list sorted, so the list can be sorted, and there is a middle value. The problem is
The only way to get to the middle is to have gone through.
I can't get to the middle that quick in one step. Even though the list could be sorted, even though there is a middle value in the list, there's no way to put my hands on it until I get from the beginning all the way to the middle, right? If I could sort this list or assume it's sorted, that will be, there's no problem in getting it sorted. 2, 5, 16, 32, 40, 50, and 50, right? There is a clear middle value. This is the middle. But I have no way to access that middle in a list. In an array, I have a way because I say, okay, I can compute the middle index, and then how does the computer knows how to read A of M again?
That's a good question.
Okay.
What number would M be if there was an even number in the list?
Right, I say here, take the floor or the ceiling. So it's not going to be exactly middle. In here, the middle will be 32. If I have another 100 here, maybe the middle will be either 32 or 40.
Okay.
So it's one of those. You have to be exact in your implementation to make sure you get it right. But it's either the ceiling or the floor of this value. So that's a small detail that only concerns engineering. Conceptually, the algorithm works the same way. You got to make sure you're getting the right middle so you don't skip values in there. Not a big deal, just careful when you implement. Back to my list example versus array. I get the middle index. How does the computer get A or M so fast? Or the operating system, or the compiler, whoever gets it, yes.
Because you start at the beginning and you know exactly how big each element is, so you can just take and take memory.
So if every element is 4 bytes, right? Because we said integers, 4 bytes by default. You can ask for 8 bytes integers, but by default, when you say I want integers, you're getting 4 bytes each. So if M is 5, how does this go? It takes the address of where the array starts in memory, moves forward, what did you say? 5 times 4 bytes. He knows exactly how to move that many bytes forward and reach the element there. He doesn't have to traverse the array. He knows exactly where this piece in memory is. So are we clear why binary search would not work with a list? I can't get my hands on the middle value right away. All right. So how fast is this? If I do this instead of the linear search, how fast is it going to go?
Log n.
Why log n? Yes, I agree. It's theta. This is our notation for roughly the running time. Log base 2 of n, asymptote. So this is the asymptote runtime. This is the same as log n. It turns out when the runtime contains logs, doesn't matter the base. The base doesn't change the asymptote. All logs have the same asymptote running time. So it's base 2 or base 10 or base 5 or base 6. It's the same as far as the asymptotic is concerned. So we don't need to specify the log 2 if we don't want to. Yes?
If we look at the runtime recursively, we can say that, like some runtime function n for n elements.
So I have n elements, right?
Yeah.
Then you do one step. I think that's what you mean, one step. After one step, I'm going to have?
The runtime of half that many elements
So it'll be n by 2 elements,
plus,
plus something, maybe a constant.
right, for the middle comparison.
This is the comparison, A of M versus V. Right? So what he's saying is, let's analyze how this algorithm actually works. We start with n elements. We do a comparison. We check A of M. It's the comparison plus the M calculation, right? 1 plus n divided by 2. There's 2 things that are going on there. That's a constant time because it's 2 operations. That's always 2, so it's constant. But what happens when I decide to ignore half of the array? The remaining, this is a loop, right? A loop. It ends here. To make this correct, we have to actually do a little bit of plumbing here. We kind of design it, we know how it's gonna work. But what happens when I move to the left side? Now I decided in here, my value A of M was too big, so I'm only moving to the left side. What am I gonna do now? Somebody else. Once I moved into 1/2, say ignore 1/2, just be on 1/2, then what? Yes.
In the middle of the
Keep repeating it, right? But now I can't do 1 plus n by 2 again. Because maybe if I move to the right side, it's not from 1 to n, it's from middle to the end, right? So the right way is to say, I have a value v in an array from beginning to the end. And then who's this now? This is the beginning plus end divided by 2. And how do I ignore the right side? The beginning stays, this is the beginning, and this is the end. So if I say I want to make the array just this part, what happens to the beginning? Remains where it was, right? It's the same beginning if I want to move to the left side. But what happens to the end? Yes.
becomes the index that you searched at.
Becomes this M. It's the middle now. So searching just the left side means my new array is from beginning to the middle. What happens in here? Beginning is now what? M. And what happens to the end? Still the end. So that's how I do the plumbing to say, well, this is a recursive call, right? This search is the recursive call in here. So this is a recursive call. Just for a smaller array. So now back to his description of how this works. Once I do one step, my size of the array, it's now half. It could be the first half or the second half, but it's only half of it. How about after 2 steps? First step chops it in half. Second step takes that half and does what? Chop it in half again. So now I have n by 4 elements, right? And then after 3 steps, meaning 3 iterations of this loop, how many elements I'm going to have left to search? This is left to, not left, not confusing with that left. Remain to search size to search. 3 steps. What's the size I have left to search? N over 8, right? So at every step, I reduce my search space in half. I cut half of it out of the search space. What happens in a linear search? At every step, I reduce my search space by 1. In a linear search, every time I move on, I got rid of 1 element in the array, so I reduce by 1. In a binary search, every time I move on, I got rid of half of the array. So how many steps until I get 1 element left? How many steps do I need to do? K steps implies 1 element left. Well, I have to n by 2, by 2, by 2, by 2. How many times do I need to divide k times to get approximately 1? Right? Because I have to divide by 2 so many times to get a 1. K has to be who?
Base 2, right?
Approximately log base 2. Right? By division, successive divisions by 2, I need to divide roughly log 2 times of n to get to a 1 element. If I'm left to 1 or 2 elements, I can just check them directly, right? Is the value that I'm looking for there or not? Good. So that's binary search. And intuitively, again, we don't have a formal definition for this theta yet, but intuitively, it's how many steps roughly it's going to take.
Is the average case also log?
Right, so he's asking a good question. The worst case, how can I get to the worst case? I divide by 2, I keep searching, and in the end I didn't find the value, right? Do I have to perform all the divisions to get to that point? If I don't find the value, I'll have to get down to 1 element and then check that element and say, not found. But he's saying, maybe lucky case is what in here, before we get to average? I found it in 1 step, right? Done. So the best case is theta of 1. That's a constant. This is the worst case. When I do all the divisions and the element is not there. How about the average case? What if the element is, somewhere in the middle with equal likelihood? It could be in the first spot, second spot, third spot. What is the average case? You have to trust me on this one for now. It's still log n. It's true that you can be lucky. Sometimes find it, you don't have to go all the way to the end because by chance one of these middle indexes is exactly the value you're looking for and you can say done. But on average, it's still going to take log base 2n steps. It's not the same log base 2n, and see I put this theta, it's like in here. One is n by 2 and the other one is n. They both linear, so asymptotically they're the same. Same thing happened here. So of course the average is going to be a little less than searching the whole thing. but asymptotically speaking, they both logarithmic functions. So you have to trust me on this one a little bit before we get to it why it is. I want to point out that this problem can be formulated in a slightly different way. And that formulation, we cause a lot of pain at exams with it sometimes, in the past. We're not going to do this year, but I want to show you how can I look at the same binary search algorithm just in a slightly different way. So say I have find my secret number x that is between 0 and I don't know, 1023, say that's 2 to the 10 minus 1. I pick some random values, and by find my secret number, I know the number. You can ask questions. Questions are comparisons. You can ask, compare x with a value v. The v is up to people who ask the question. X is my secret number. You can pick a v and say you get 3 answers. X equal v, you get x bigger than v, or x smaller than v. So if I tell you I have a secret number between 0 and 1023, an integer, what's the first question? What's the first v you need to ask? Right. So the binary search algorithm is the same algorithm. Instead of looking through, it's looking for a value that's a secret value in this array from 0 to 1023. The first question will be compare x, which we don't know, with what v? 512, right? It's roughly half. The reason we want this value and not a different value, we want to maximize the chopping off of the search space. The search space initially, how big is it? How many possible secret values are there? 23. We want to chop that space in half. Of course, we can be very lucky and pick a value that it's exactly x, and then we're done. But let's assume we are not that lucky. What's the problem of saying, somebody says, wait a minute, if I ask compare x with 20 instead, I could be very lucky, right? What would be the lucky answer in this case? Less than 20. Bingo, right? Like how many values are left? Less than 20. I chop off what? 1,000 values of my array, right? The problem with this question is, chances are, you are not lucky, right? If x could be anywhere between 1 and 1023, what's the chance to be less than 20? And what's the chance to be bigger than 20? How much represents 20 out of 1023, roughly? 1 in 51. So the chance of being smaller than 20 approximately is about 2%, right? So if it's uniform distribution, the probability of the answer being x is less than 20 is about how much? 2%. Probability of x equal 20 is about 1 over 1023, to be exactly that value. And the probability of x bigger than 20 is about 98%. So hoping to be lucky is the same thing, the same reason people buy lottery tickets, right? Did you buy lottery tickets? Everybody who buys lottery tickets does not understand statistics. That's an absolute crude test for, you see somebody buying lottery tickets, you say, you need to take some statistics classes, buddy, because you're never going to win the lottery, okay? And they say, wait a minute, how do you mean? Somebody always wins the lottery, right? It's in the news, I've seen it, right? What's the chance that I win the lottery? 0. 0 point something theoretical, but that's still a 0 in practice. So I never buy lottery tickets. right? Because I took a lot of statistics classes in my life. So why we don't ask this question? It's true we can be lucky, but the chances are 98% of the time we are lucky, and in this case, how much I cut off of my search space if I get this answer? How many values I took out of my array? Just 20 out of 1,000 values. That I still have to search 1,001 values, right? So the search space in here, it's, of course, I'm very lucky. In here, it's nothing done. And in here, I still have 1,000 values to look into. That's why I like this answer. What's the situation in here? I can be lucky and get the value, bingo. Let's assume I'm not lucky. Either way, whatever comes negative or positive, the search space is reduced in half. That's why I like this question. This is not good. This is good question, because in here, 50% of the time, or the other 50% of the time, the search space will be now 512. Either way, x bigger or smaller, I've got chopped my space in half.
Wouldn't you want to use 511 since it starts at 0?
Sure, approximately. Depends how you look at this comparison, because there's a case where it's exactly 512. And then you have on one side 511, on the other side 512, because the total from 0 to 124, that's 1,024 values. One is exactly this one. The remaining ones are 1,023, 511 on one side, 512 on the other side. In algorithms, we don't care about these picky little details. What you have to care about those is when you implement an algorithm. When you actually put it in Python or Java, you have to be very careful with those cases. In terms of the running time, obviously, it doesn't matter if it's 511 or 512 search space. The number of steps I'm going to take is roughly the same. Right. So how does it look in binary? I think, hands up, who's understanding what's going on here. To guess my secret numbers, how many questions going to take? Question 1, question 2. Question 2 will be what? Compare the value x with what? Well, it depends, right? If this one goes left, if the question 1 says go left, then this value here, V2 will be who? If I move to the left side of the space, 256. And if the question 1 says go right, then V2 will be who? 768. That is 512 plus 256. Okay. So now what I want to say, well, how do I, and then dot, 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 right? The total number of questions will be log base 2 and n is 1023 here. Questions. So now, what happens in binary? I do the same exact problem in binary. I look at my representation x, how many bits it has. How many bits are here? This is 10 bits. Because it's between 0 and 1023, right? 1024 will need 1 followed by 11 bits. What is the first question effectively asking in binary? Is it bigger than 512 or not? How do you translate that question in binary? Somebody else. Yes? Is the first bit, so question 1 is first bit 1 or 0? If it's 1, it means the number is at least 512. If it's 0, means the number is at most 512. So those are the left and the right sides in decimal. What's the question 2 asking effectively? Actually, either way, left side or right side, question 2 is asking the same exact thing in binary. What is this question asking if I had to move to the left side? Is the second bit 1 or 0, and this question is asking the same thing. Is the second bit 1 or 0? So question 2 is second bit 1 or 0? So now you can see, maybe more visually, how this strategy works. What's the first bit? What's the second bit? What's the third bit? What's the fourth bit? So on and so forth. I ask how many questions? 10 questions, which is exactly log of 1024, right? And then I know the number. How do I guess the number? Well, I have the bits.
Just make the bits.
So whatever comes 0, 1, 0, 1, 1, 1, 0, 0, 0, that I transform that in decimal, that's the number. These questions, the reason it's called binary search, it's effectively asking the binary bits of the number. Can I do the same thing in decimal? How do I mimic this stuff in decimal? How do I say, I have a decimal number, this is decimal, suppose my x is 1, 0, 1, 2. How would I do these questions in decimal? What do I have to ask? Is the first digit
What is
1? No, I can only answer questions that are true or false, like that way, that way. What do I have to ask? Is the first digit 1? If it's 1, if I get the answer yes, then I move to the next digit. If it's 0, can I have any other possibility for this digit than 1 or 0? No, because this is 1,000 digits, so it's only 1 or 0. But how about this one? If I ask if it say 9, I get the answer no. I have to ask now if it's 8 or 7 or 6. So how many questions I might need here? 10 questions. And here, how many questions I need?
10.
And here, another 10. So this will be a total of 30 questions in decimals. Is it better than linear search? These 30 questions in decimal? Definitely better. Linear search, how many steps will I take? 1024. This in decimal, asking for each digit exactly to guess the value, would be only 32 questions maybe. It's better than asking 1024, but not as good as binary search. Binary search does it in 10 questions. This will do it in 30 questions. So there's some algorithms based on this idea.
With the decimal, do you have to ask them, like, is it 1, is it 2, is it 3, is it 4? Can you ask them, like, is it greater than 5, or is it?
Right, if I start asking questions like greater or 5 or less than 5 for each digit,
Yeah.
I get closer to binary search, because now I don't need 10 questions for each digit. If I do binary search, I need like 4 questions for a digit, right? Because I need log base 2 of 10. So that's still more than the binary search because I do it digit by digit, but better than asking each linear search for each digit. So we've done binary search. And now I want to do, there's a bunch of slides here that you can go through. This is the search stuff. The other stuff that we need is the sort stuff. So how do I now sort? Sorting is more difficult than searching. Searching is only saying, give me one value from the array if you can find it. Sorting is saying, you gotta sort this array or list in order. So suppose I have an array here or a list. My array is this is a different array, 6, 3, 7, 9, 5, 0, 1, 8. I don't put the indexes. The indexes will be 1, 2, 3, 4, 5, 6, 7, 8. And these are the values. So here's what I can do. I can do selection sort. Selection sort says find, start with an index, say I equal 1. Actually, no. Let's do it. For I equal 1 to n. Find minimum in A. And then put the output of I equal that minimum. And then I'm going to write something in English, block minimum found. So it's never find again, never found later. So how this works, output, I'm going to say here except blocked values. So here's the output. It goes from 1, 2, 3, 4, 5, 6, 7, 8. The first one is the minimum in the array. What's the minimum? 0. And I'm blocking. This dot means block. Now I'm looking again at the minimum of the array, but I can't use the blocked elements. So what's the minimum except for the block one? 1. I'm blocking the 1. What's the minimum except for the blocked elements again? 3. I'm blocking 3. Then what's the minimum? 5. I'm blocking 5. Then 6. It's blocked now. I'm left to it 7, 8, and 9. So what's the next one? 7. Blocked. 8. Blocked. And then 9 is the only thing left. How many people understand selection sort? Find the minimum, write it down, move on, find the next minimum, because you exclude the blocked element. So if somebody needs to figure out how to engineer these blocks, right? If you had to write a computer program to do this, you have to figure out a way to keep track of who's blocked and who's not blocked, right? It's essential to not find the same minimum that you found before. It has to be a different element. So every element that's put in has to be blocked for further searches of the minimum. How long does it take me to find the minimum? The minimum is like maximum, right? How long is it going to take me? Roughly 8 of n, but it's not the same n because of this block stuff, right? But let's say it's 8 of n. Not very rigorous. That's just this line, find the minimum. How many times I'm going to do this? How many times I'm going to find the minimum? N times, right? So this is n times. The runtime in here is going to be n times n squared. Again, this is this asymptotic runtime. We don't bother too much with how it works rigorously.
Since you're taking one value out, percent like your blocking value, why would it not be n equal or like
n plus n minus 1 plus n minus 2.
Yeah.
In principle, that's possible that this time will decrease. But in reality, I still have to go through all of them to check the block, right? I mean, you're right. If I find a way to exclude those blocks ones, like I never look at them, the next time is going to be n minus 1, the next one n minus 2, n minus 3. But in reality, I'm still going to go through all of them, just check if it's blocked or not. If it's not blocked, I consider it in my mean calculation or comparison. If it's blocked, I just move on.
If it was possible to discard the blocked values, what would be the formula for?
Like in the list. In a list, I'll have to, every time I block something, I don't actually block it. I remove it from the list, right? That way I don't have to worry about the blocks. So in that sense, what's going to happen, this is going to be n plus n minus 1 plus n minus 2, right? That's what you're saying.
Yes.
Suppose no worries about blocks. Actually, let's write that as block means remove. So for a list, if blocks is removed, the runtime is going to be n for the first time of the loop. Then it's n minus 1, right? Plus n minus 2 plus 1, right? The first time I go through n elements, second time I go to only n minus 1 elements, n minus 2. That is n times n plus 1 by 2. It's still roughly n squared. Again, this is this n squared is smaller than this n squared, because you can tell n times n plus 1 by 2 is smaller than n squared. But in terms of asymptotic time, which is what I'm going to talk about in a second, they roughly all on par with n squared. How about insertion sort? Insertion sort starts with the first element, the 6, and then puts the next element next to it, 3. And what it does, it says move 3 to the left until correct position. So it's 3 in the correct position as far as 6 goes. Is it or not? No, I need to move it once. I need to move, to do this, I'm going to get 3, 6. So how many swaps? Move 3 to the left. This is by swapping or bubbling. How many swaps I need to reverse 3 to 6? 1 swap, right? And then I have 3, 6. I do, that's step number 2. Step number 1, step number 2. I get 3, 6, that's my partial array, and I'm adding to it the next value, that's the 7, right? Right there. And I got, now swap 7 to left until, this is 1 swap here, until correct position. Is 7 in the correct position? Do I need to move it to the left or not? It's 7 in the correct position here. Yes. So that's no swaps. 3, 6, 7. Keep going. I have 3, 6, 7 now. Observe that this array is already sorted, partially sorted. Everything I've got so far is sorted, right? And I'm adding the value 9. That against, I'm going to just do it like that, no swap. How about 0? 3, 6, 7, 9, 0. This is sorted, this is 0 added in. Do I need swaps? Do I need to move 0 inside? Yes or no?
Yes.
Yeah, so this would be 3, 6, 7, 0, 9. That's 1 swap. Then this is going to be another swap. What's the next thing? 3, 6, 0, 7, 9. Then another swap. 3, 0, 6, 7, 9. Do I still need swaps? Yes, I need one more swap. 0, 3, 6, 7, 9. Now how many swaps will happen here? 4 swaps. And keep going with the 5. So I now have 3, 0, 6, 7, 9. That's my array. I'm adding 5 to it. How many swaps are needed to move 5 in the correct spot? It will be 3 swaps, right? 1, 2. I need to move 5, swap 5 with 9, then with 7, then with 6. 0 is here, 3 is here. How many swaps do I need? The end result will be 0, 3, 5, 6, 7, 9. Do we see how this algorithm works? To put the element at the end, they just swap it in. Hands up, who's me? On insertion sort here. I want to do a variant. How can I do this in a list? So this is for the array. Suppose now I have a list. Yes. Put it at the end of the list and just swap it in with the previous. I need to know the previous, so it'd be useful to have a double linked list. Because the list, the way I draw it, just goes to that side, but how do we get it, the previous element to swap to, right? We need to compare. The reason we know to stop here is we compare the 5 with the 3, and we say 3 is smaller, so you don't need a swap in there, right? in here, if I do this with the list, so there is two things with insertion sort that are happening. The two things is find the correct spot for new element and put it in. You have to make space. As it turns out, I could have find the correct spot much faster than I did. How do I find the correct spot? I go swap, swap, swap until no swap was necessary, right? That's how I did it. Could I have found the correct spot faster? I have this 5 and this array which is already sorted. Can I figure out faster than this where to put it? How? Could I have found the position with binary search? Would that have been faster than this? This is a linear time operation, right? Swap, 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 swap. It's a linear go through the array. If you find, if somebody will tell me you need to put 5, it's going to end up in the 3rd position here. That could be done faster because the array is already sorted. So I can call binary search. But what's the problem? Once I have the spot, yes?
Inserting it still takes time.
I have to move these elements to make space for it. This is a subtle point about insertion sort. Finding the spot, it's easy. You don't have to do all the swaps. But making space to put it in means moving half or maybe more than half of the array around. Are we understanding that issue? I could have found the spot faster with binary search, but I couldn't have made space for it. How about in a list? If I do a list instead, let's take that list. 0, 3, 6, 7, 9. 0, 3, 6, 7, 9. And then I added the 5 here. That needs to be swapped. How about finding the correct spot and making space for it? About those two steps. If I want to replicate insertion sort, it seems to me that I can do the other stuff very easy. Inserting the value. If somebody tells me you need to insert it between 3 and 6, right? I could insert it immediately. Is that right? In a list, I could just place it in. However, the difficulty in a list is finding the spot, right? So for an array, for the arrays versus list, those two are looking like a table like that, right? Those two items here. Finding the current spot in an array is easy. In fact, it's log n, right? Binary search. But how is it moving space and putting the element? That's hard. In a list, finding the correct spot is hard because you have to traverse the list. But placing the element, making space for it, putting it in, inserting it in is easy. Actually, it's constant time, right? Once you have the spot, putting the element there is nothing. Hands up who's with me on this. In an array, it's easy to find a spot, but hard to insert it. In a list, it's the opposite. It's hard to find a spot, but very easy to insert it. Right? So, find the spot for 5 is linear time. But then insert 5 and the spot, that's constant time. Because I just put 5 in there and make it to the list. Is there something else than an array on a list that allows me to do this? So because one of the steps is linear, either this step is this step, and I do it for n elements, what's the running time of insertion sort? If each, in the arrays, this will take linear time, because I have to move all these elements. In the list, finding the thing will take linear time, and I have to do this n times, because I do it for every element. So the running time for insertion sort is? Either list or arrays. You can't, one of the steps will be linear, you have to repeat it n times, so n times n squared, roughly. Can you do something intelligent here? Is there a way to organize my data that's neither a list or array to make both operations fast? tree. How would I look in a tree? I'm going to do the whole array here. How do I organize this array in a tree? I start with 6 at the top. Where 3 goes? This value. I insert it in here, the left. The left side, so with the tree, it's called a binary tree. The left, it's always smaller than the node, smaller than the right. That's the, so where is the 7 gonna go? 7 gonna go here because 7 is bigger than 6. How about 9? Keeps going down. Here's 9. That 9. How about the next one, 5? How is 5 compared to 6? Smaller, but how is compared to 3? So where this goes like this, 5. It's still on the left side of 6, but on the right side of 3. How about this 0? Where is this going? Smaller, smaller, 0 right here. How about that 1? Compared to 6?
Smaller.
Smaller compared to 3?
Smaller.
Compared to 0? Here's the 1. How about the 8? Compared to 6?
Bigger.
Bigger. Compared to 7?
Bigger.
Bigger. Compared to 9? A tree has some properties of the arrays and some property of the list if you know how to manage it. Management is far more complicated. But can I achieve both operations faster than linear? How long is going to take to find the correct spot, this operation? Find the spot where you need to put the value. What's this related to in a tree? What's the maximum number of take it can take me to find? If I always start from the top, and in the worst case, I'll have to go to the deepest branch, right? So the size of the tree will dictate how long it's going to take to find me the spot, right? So find the spot takes how deep the tree is. How about inserting it, putting it in? How long does it take? Once I know I need to put it here, how long does it take to put it? Constant time. Right? So it's the finding the spot that can take time. So what do I have to do with this tree to make it work better than a list? Because in a list, finding the spot is linear time. In a tree, what property the tree needs to have to be faster than linear time to find the correct spot? It's always undirected or directed. It's always from the root down, right? Yes.
It has to go less than n values. Let's go to less than.
Yes. But how do we say that?
We can search with the binary search.
What?
Or we can use a binary search to find the element.
I can use binary search on the tree. My point is that the tree might look like a list if I'm not careful. Right? It's possible that the tree is go left, 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 left. That's essentially a list and nothing else. This tree must have a property to allow me to find it in logarithm time, right? The depth of it has to be logarithm. What do you want to say?
Never mind. I was just gonna say that all the like it has to be sorted, or like all the nodes in the left branch of the tree have to be.
The tree is always sorted. Well, elements that I've gone through is the same like in all insertion sort. The elements I've gone through, they are sorted. Because you can see there is a way to read this thing from the left to right to get everything sorted here. Yes?
The root has to be like in the middle. The root can't be the biggest.
Not just the root. The tree on overall has to be balanced. We did something related at recitations about it. All the paths from the root to the base, to the leaves, have to be roughly log n. If I have a really long path, I could be unlucky and go through that path, and that's linear time now. So for this to be efficient, find spot is logarithmic time, and insert is constant time. But the tree has to be balanced. It can't have very long branches and very short branches. It has to be roughly balanced. So in algorithms, we talk about algorithms to balance the trees that get out of balance. This is a very useful structure if it keeps looking like a tree as opposed to a long list on one branch. So we need algorithm who takes unbalanced trees and balance them. That's a red-black tree. If you're going to study in algorithms, how do you balance a tree to make sure none of these branches are very long as compared to other branches? So that's insertion sort. You can optimize election sort. If I do this, and if I make sure it's balanced, so the finding is log n, what's be the runtime here? I have to do this for any element, for all elements, so it's n times. But instead of n times n, this is going to be n times log n. So that's going to be a better runtime. If I do this, I'm going to get n log n time. Of course, I have to read it. I have to find a way to read it in order now. But that's easy. Another algorithm that everybody knows already is called merge sort. Merge sort says, I'm going to take my array right there, 6, 3, 7, 9, 5, 0, 1, 8. I want to sort it, of course. I'm going to chop it in half. It's like a lazy sort. It does the chopping and sorting later. So it says, okay, now I have 6, 3, 7, 9, and separately 5, 0, 1, 8. I want to sort these ones. How do you sort them? Well, I chop it in half. I do 6, 3, 7, 9, and then on the other side I have 5, 0, and 1, 8. So if I'm at 6, 3, I'm going to sort this directly because it's a very small chunk. I'm going to say 3, 6, 7, 9, this is 0, 5, and this is 1, 8. Right? It's already sorted. I don't need to sort nothing. But then I kind of put it back. I say, okay, in here, those two, you got to merge into a sorted thing. So in here, how do I have to find a procedure to say if this is sorted already, sorted, and this is sorted, how do you put it back? The answer is going to be 0, 1, 5, 8 via merging. So I have an algorithm that says, okay, look at those two sorted sequences and combine them together into a merged sequence. And how about those two? When I put these together via merge, I get 1. What sequence do I get? If I merge them, this is sorted, but I have to interleave them now properly. What's the sorted sequence here? 3, 6, 7, 9. And now I'm looking at 3, 6, 7, 9 and 0, 1, 5, 8. That's sorted. This is sorted. So how do I get to merge them? If I merge those two sequences, what do I get? 0, 1, then I get this 3 from here, then I get the 5 from the other side, then I get the 6 from here, 7, 8 from the other side, and the 9. So this algorithm proceeds down by breaking stuff into parts, and then once the parts are very small, they get sorted, because sorting two values is very easy, right? Just a swap, maybe, or maybe no swap. But then it brings everything back in a way that's being merged. If I have two sequences that are now sorted, it combines them back to sorted things. So how do I write this recursively? I have my array A input. I have to get the left sorted. I'm going to sort, I'm going to say, this is called merge sort, right? I'm going to call merge sort on the left side, A from 1 to half. and the right sorted, I'm going to call merge sort, which is a recursive call from half, maybe plus 1, half to the end. So this is one side of the array, that's the other side of the array. Now that I have the left sorted and the right sorted, I have to create an output which is merge sorted left sort and right sort. And this is a merge sort procedure. The trick part is in the recursive call right here. So I wanted to show to you first what happens in action so you can follow the procedure. Merge sort, because it's a recursive call before the actual merging happens, it's going to keep splitting, right? I need a base case somewhere that says if the array is just of size 2, don't do this anymore. Just either leave it in the order it is if it's sorted or swap it. So I need a special case if the size of A is 2 or less, sort manually. That will be when I get to these places. I don't keep calling merge sort on it, I just sort it by hand. But do people see how this is going? I split, so I start with the split. This is my array, split, split, split. When I get down, each procedure now, I have 4 threads in here. Each procedure sorts, and then the merge will put them back together. 3, 6, and 79 becomes this. 0, 5, and 18 becomes that. So now I'm returning back to the calling procedure. And when I join them again, the outputs of the previous 2, I join this output and this output. But the merging has to respect the order, interleave them properly. So this has to be a procedure that I need to define. How do I take 2 sorted arrays and combine them? Is there a way to do that? How would you do it? I get 2 sorted arrays, and you have to put them together. How can you do such a thing? Yes.
Compare the first value of each.
Right, like for example, 3 and 0. And we decide what? Who's smaller? 0, right? Put the 0 in and then advance the 0 index to 1. And now what do I compare? 1 and 3, who's smallest?
1.
Put it there and then advance to 5. Now between 3 and 5? 3. I put the 3 in and I advance here to 6. Now I have 5 and 6. 5 goes in, I advance to 8. I have 6 and 8. 6 goes in, then 7 and 8.
7.
Then I have 8 and 9. 8 and then the 9. How long is going to take that procedure to do these 2 arrays? Is that the linear time operation? Yes. So this is linear. However, the runtime of merge sort can be, it's hard to measure because it has this recursion in. If merge sort takes t of n, I don't know how big is t. Is t of n. How long is this going to take? Right here. How much? T n over 2, right? We don't know what the runtime of merge sort is, but if it takes so much time for n, then it's going to take so much time that function t for half, because this is just half of it. And then t of n over 2 here. The only thing I can say about merge sort is that it's 2 times t of n by 2 plus something linear. How many people see where this is coming from? Hands up. So where's the 2n by 2? Well, I need to do half of it, then another half of it, right? Then put it together, that takes time, and that's how I get my merge sort total running time. Right? Again, if I have 100 elements, merge sort for 100 elements is going to be merge sort of 50, that's the first half, merge sort of another 50, that's the other half, that's twice times merge sort of 50, plus how long it takes to put them together, the 50 and 50, which we know it's a linear operation. Now this is not yet in theta form, it's not a closed form. This is a recurrence like Fibonacci is defined in terms of previous values, not exactly previous, but half of it. And we have to find out what kind of recursion this is. There are other sorting procedures. We have quick sort, bubble sort, bucket sort, counting sort, radix sort, a lot of sorting procedures in computer science. One thing that I have to say before we finish, that's going to take, we have 2 minutes left, it's going to take 3 minutes. But just 1 minute over. It's something we need to go by, do Friday in class, so it's not a big deal. But just in case you want to do the homework right now, like today, you can't wait until Friday. Here's what's happening with these functions, fees and stuff like that. We say a function t of n is theta of n, like we said, or n squared. We said there. This is the insertion sort or the selection sort running time. Because t of n is between some constant of n squared, and on the other side it's also a constant of n squared. That's why we're not concerned with whether it's, think about n squared is definitely within constants of n squared. But also n times n plus 1 by 2, it's also within constants. Can anybody give me a constant that works here? 1 times n squared, is that correct? Can anybody give me a constant that works here? 1 by 2? So we say they both n squared because it's in constants within n squared. The same thing will happen of n squared by 5. That's obviously n squared by 5 plus 3n plus 2. That's within some constant of n squared and within some other constant. This is constant number 2 of n squared. Even though this is a polynomial of degree 2, you can find a constant such that n squared is bigger than it, and another constant, very small, that it's always smaller than it. So that's what theta means. In general, theta of a function g of n, this is t of n, means t of n is between some constant of g of n and some other constant of g of n. And we say they have the same asymptotic growth because this function is within constants of the other function. They're both n squared or n log n. Now, it could be that we can't do both sides and we only have one side. For example, n log n, that's my t of n function from the merge sort. How does it compare with n squared? Which one is bigger? N squared. So I can definitely say this is smaller than a constant times n squared. For sure. What constant would that be? 1. Right? Can I say it's bigger than some other constant times n squared? Is there a constant that I can put here? Something very small, 1 over a gazillion. And make it, this is bigger than n squared times a constant. No. Whatever constant you choose here, n squared will always be bigger, eventually. Because you look at the plots, right? You look at the plot and say, how it's n squared going? This way. How it's n log n going? This way. No matter what constant I pick, that function n squared will eventually beat n log n. This is impossible. So how do we still say something about n log n versus n squared? We can't say theta. Theta means they're within constants of each other, roughly the same asymptotic growth. Fine. So how do we say something about this? We don't use theta. We say n log n is, it's called O of n squared. So O versus theta, be careful, it's just missing the middle line. That's it. It means I can say that n log n is at most n squared times a constant, but I can't say the other side. The other side, we say there's another symbol that we need just for the left side. For example, if I want to say, how's n squared compared to, say, n cubed versus n? N squared is definitely at most n cubed. How do I say here? N squared is definitely bigger than n. The symbol I need is this big omega, So theta is, I'm done. Theta is when it's the same within constants. O is only one side, omega is only the other side. So your homework contains about a small exercises about this. We're gonna do this on Friday. This part of the homework is the easy part. The hard part of the homework is the strong induction part. So for that, we don't need to worry about the thetas and omegas.
For today. Right? It's our homework. That would have been,
My buddy, he came in clutch with lateral and take it on like Saturday and just see how far I can get. I know. And is it bad? I mean, that's is it unethical?
but I've never taken it back.
What?
No. I've picked it up a long time.
So it writes it to the file, it'll track the how you're using it and it'll keep adding to it. But I haven't written it yet, so it just